Hello grade 11s and welcome to this theory video on the electric field. In this video we will only define an electric field and we will speak about the direction of the electric field. In the next video we will see how you can use different formulae to calculate electric field strength. We say that an electric field is a region in space in which an electric charge experiences a force. In other words, when an electric charge is placed in an electric field, it will experience a force. That force is called the electrostatic force, and we can calculate the magnitude of the electrostatic force by making use of Coulomb's law. To calculate the magnitude of the electric field, we have options. We can either use formula 1, E equals F divided by Q, or formula 2, E equals KQ divided by R squared. We will speak about these formulae in the next video. But for now, we're going to focus on the direction of the electric field. Electric field has magnitude and direction. And to determine the direction of the electric field, we cannot use the formulae. Instead, we say that the direction of an electric field at a point is the direction that a positive test charge will move if it is placed at that point. So we use electric field lines to draw or represent the electric field around charged particles. If we are looking at a positive point charge, then to determine the direction of the electric field, we will take a positive test charge and place it in the electric field of this positively charged particle at the center. Since positive repels positive, we expect this positive test charge to move away from the positive charge at the center. And therefore, we have that when we draw the electric field lines, they all point outwards or away from the positive point charge. If we have a negative point charge, then if we put a positive test charge in its electric field, we know that since positive and negative are unlike charges, they are going to attract each other. The positive test charge will therefore move towards the negative charge at the center, and it is for this reason that the arrows on the electric field lines point towards this negative charge. We can therefore say that when we draw the electric field lines around charged particles, number one, they must be drawn perpendicular to the surface, and number two, they point from positive to negative. If you look at these lines, you will see they're all at 90-degree angles to the surface of the charged particles. But also they point away from the positively charged particle, and they point into or towards the negatively charged particle. We therefore say electric field lines point from positive to negative. Now sometimes we're going to provide you with two charged particles and ask you to draw the electric field pattern that surrounds them. For example, we may give you a negative and a positively charged particle. As you can see here, the lines still point away from the positively charged particle, but they point towards the negatively charged particle. The rule still remains the same. Sometimes we will give you two charged particles that have the same charge, like two positively charged particles. In this case, you can see that the field lines point away from the positively charged particles. And that is because positive test charges that are placed in these electric fields, they are going to move away from these positively charged particles. Now, of course, sometimes instead of giving you two positively charged particles, we can go and replace these positively charged particles with negative charges. In this case, we know that the positive test charges are going to move towards the negatively charged particles, and the arrows therefore have to point inwards or towards the negative charges. The shape of the field stays the same, but the direction of the arrows is going to change, because field lines always go away from positive and towards negative. There are a few other points that we use to guide us when we draw these field lines. We have that the field lines never cross or touch each other. So if you draw the electric field pattern surrounding a charged particle and you do something like this and you let them touch each other, you're going to lose marks because they are not allowed to overlap or touch each other. We also say that the closer the lines are, the stronger the field is. So if you look at the drawings over here, you're going to see that at this point, closer to the negatively charged particle, the field lines are drawn relatively close to each other. But over here, at a certain distance away from the negatively charged particle, the distance becomes larger. That is because the field closer is stronger than the field further away from the negatively charged particle. If we put a positive test charge in this field, it will experience a stronger force over here versus here further away from the negative charge. We then look at the the last point. Since we live in a three-dimensional world, we have that the electric field that surrounds different charges is three-dimensional as well. So what that means for us, since we answer questions on paper, is that whenever you draw the field lines, you need to show them around the entire charged particle. What I often find is that learners draw what is between the particles, but forget about what is on the outside or what surrounds them, and they therefore lose marks. So just remember the last point, that these electric field lines, or the electric field, is three-dimensional, and that is why in 2D we need to draw the lines all around these particles. So let's say that we give you a charged particle. I'm going to start off with a positively charged particle, and we say to you, determine the direction of the electric field at 1 meter towards the left of this positively charged particle. To determine that direction, you're going to go and find 1 meter towards the left of this charged particle. Let's say that 1 meter is over there. Then you're going to say, if we put a positive test charge at this point, in which direction will it move? Since positive repels positive, we know that this positively charged particle is going to move to the left, away from the positively charged particle at the center. And we therefore say that at 1 meter to the left, the field line is going to point towards the left, or the electric field is towards the left. If we then say determine the direction of the field 2 meters to the right, we'll do the same thing. We go 2 meters towards the right of this positively charged particle. We then take a positive test charge and we place it at that point. And we say, in which direction will this positive test charge move if it is placed at that point in the electric field of this positive charged particle at the center? Since positive is repelled by positive, we expect this positive test charge to move away from the positively charged particle, and therefore it will be pushed towards the right. We therefore say that if a charge, or if we are required to determine the direction of the electric field 2 meters towards the right of this positively charged particle, it will be towards the right. Now let's go and replace this positively charged particle by a negatively charged particle like this. So here is our negatively charged particle. Now we say determine the direction of the electric field at 1 meter to the left. Here's 1 meter to the left of this negatively charged particle. We place our positive test charge at that distance away from the negatively charged particle. And we say, in which direction will this positive test charge move? Since positive is attracted to negative, the positive test charge is going to move towards the right. And therefore, to answer A, we're going to say towards the right. If we ask, in which direction is the electric field at 2 meters to the right of this negatively charged particle, we do the same thing. We place our test charge at a distance 2 meters to the right of this negative charge. And we say, in which direction will it move? Since positive is attracted to negative, it's going to move towards the negative charge, and therefore it will move towards the left. The electric field is therefore towards the left. This is how you're going to determine the direction of the electric field. You can either draw the entire electric field pattern around the charge and then go a certain distance away from it, or you place point charges in that electric field and ask yourself, in which direction will a positive test charge move?